Hello everyone. Last time we started talking about acoustic gravity waves. We've discussed the equations that govern the problem. We said that we can use the wave equation, which was a given, with c there being the speed of sound in the water, and it's a two-dimensional problem that we're solving now. And we discussed also the boundary conditions. What happens at the sea surface? We said that there are two conditions at the surface, one kinematic and the other dynamic. And at the bottom, we're solving a simple problem where the bottom is just with the constant depth first, and also it's a rigid bottom. To start with, we said we're going to ignore compressibility, and as a result we lose this term here, right? So it's no longer the wave equation really, to have phi xx plus phi zz equals 0. And we use separation of variables, and we found the dispersion relation here. Now, what we're going to do next, this is the dispersion relation. And of course we went back and found the velocity potential. And we said if you want now to find the velocities, all you need to do is take the derivative. I can actually type this down here. So now if you want the velocity in the x direction, u, so u is phi x, and that would simply be the derivative with respect to x here. Okay, so you have, let's take the real part now. So you're gonna have k times, so omega eta 0 times k, and we lose the k here, and the rest is the same, hyperbolic cosine kz plus h over hyperbolic sine what is that? There is no z here. There is no z here. That's a mistake. Let's correct that. Okay. This should be kh. This is constant. Okay, so we have kh times cosine kx minus omega t. So this is the velocity in the x direction. And the same thing we can do for w. So w would be phi z. We have a k here. The same thing, it would go out there. You're going to have a hyperbolic sine instead of the hyperbolic cosine. So we have omega eta 0 hyperbolic sine kz plus h divided by hyperbolic sine kh, and here we have sine kx minus omega t. Note that the potential here, the velocity potential, decays exponentially with depth. You can see this here in the hyperbolic cosine, which means that any effect that you have, you would mainly have it on the surface. In other words, you can think about it. If you're swimming, for example, if you're diving, you might be able to feel the pressure from the waves if you have very large waves. But as you go inside, deeper and deeper inside the water, the effect decays exponentially. And that's why, in fact, if you have, even if you have very large waves, if you have storms in the ocean, and you go deep enough, maybe tens of meters, or a maximum of maybe 100 meters deep, right? You would feel nothing from the surface, because the effect is almost localized to the surface. And you can see this here in this hyperbolic cosine. So in the case of a surface gravity wave, the pressure decays exponentially with the depth, and the velocities as well. Now we want to look at the case with the general case. That's why we've been doing this. So we're gonna redo everything. We won't redo everything really, because you're gonna see that I'm gonna make some shortcuts here. But I will ask you to complete this. We want to solve the case where the compressibility is taken into account. So this term is not zero. So here we have 1 over c squared phi tt. This is what we would be solving now. The boundary conditions are the same. We're not changing the boundaries. So this holds and this holds. And we assume that eta also at the surface behaves in the same way. And this also holds, right? So what do we do now? We do the very same thing that we did before. We start with the separation of variable. But now what we get is different, because the solution now for the problem is no longer this here. We have an additional term. I can add it here maybe now on this side. We'll have phi tt over c squared. So phi tt is going to give us minus omega squared, right? Is a minus is a plus, and you have the I squared is a minus. So phi tt gives minus omega squared, and we have c squared there, f. So now we have this additional term. So all we need to do really now is bringing this term to this side. So it looks like everything is quite straightforward. So if I bring it here now, what we would have now is I'm going to write it in this way, k squared. So we still have the minus sign here, and minus omega squared over c squared. And here we're going to have f. And this all equals 0 now. Okay, so this is the new equation that we want to solve. But you see, this is not much different from what we had before. It's just instead of k squared, we now have this, which we can call new k squared. I'll just call it lambda squared, so we don't confuse between the symbols. So basically the solution, the general solution, would be looking exactly the same, but not with k. Now I'm going to do it in red to emphasize that. It's going to be with lambda. And this lambda is defined as this. I'm going to write it here. So lambda squared is k squared minus omega squared over c squared. Okay, so now we have a very similar equation, but instead of what we had before, we have lambda squared instead of k squared. That's all. So the general solution would also look the same, but with lambda here. I hope you agree with that. We use the boundary conditions, and the boundary conditions are the same, right? So this is the same boundary condition here. This would be the two new boundary conditions after substituting the function. So what we expect is really, and I would like you to actually do that without, do it from scratch, is to get the same result, but instead of k being the wave number, we'll have a lambda here. Right? It's the same differential equation, the same boundary condition. Is just instead of k we have lambda. That's all. But this difference is apparently is very important physically. And this is what I'm going to discuss now. So this is the solution. Now you know the solution. This is the general solution that you can have when you're including compressibility. And this now has all the possible waves that you can have with the given assumptions that we made here. So what do we have now really? Let's look at these. I'm going to erase this. I can type here, you know what, this is the solution, right? So I can also type here the general solution, so you can have it. So instead of this k here, you're gonna have a lambda, and instead of this k here, you will have a lambda, and I don't need this, okay? You know that you need to go to the to take the real part at the end. Okay, so this is our velocity potential, and you know that the velocities would look the same with lambda here and lambda there. Okay, you don't need to change them now. So what do we have now? What difference this makes? Okay, let's see what difference this makes. I'm gonna start from here. Having lambda squared, I'll write it here again. So I have lambda squared equals k squared minus omega squared over c squared. Let's think about it a little bit. When we talk about normal waves, now what is a normal wave? The standard waves that we're used to. K is normally small, but it's not terribly small. Okay, it can be even order 1. The frequency can be also order 1. But c squared, c is 1,500 meters per second, and this is c squared, so this is a very large number down there. This whole thing is very small. And now you see why people would actually neglect this term when they discuss waves that are order 1 compared to that term. So in other words, this term is much smaller than k squared, and therefore lambda squared would be just simply k squared. If you do that, really, what you get, if we do that, if we just substitute lambda equal k, then you get back what we had before. So that would be the surface gravity wave. So the first thing that we notice is when lambda, we're going to call it equal lambda 0, that would be almost like k0. With a very small correction, negligible to most practical reasons. And in this case, what you get is this same dispersion relation. I'm going to write it down here for a reason. So you get omega squared g k0, let's type k0, hyperbolic tangent k0h. So this is what essentially we had before, and now you can analyze situations where kh is very large or kh very small, and then you can also derive the phase velocity in these cases, as we did before. Now, look here. The difference between this dispersion relation and the dispersion relation that we had before, which looked like this one, is that here there's one solution for this dispersion relation because k is real. Okay, if k is real, we have this one solution, and that solution is the surface gravity solution. But now yes, we have the first solution is very close to that solution, so almost identical to that solution. But lambda doesn't have to be real. Lambda can still be real, lambda can be imaginary, but with real k. And you can see this here. When k squared is smaller than omega squared over c squared, that's a scenario where k can still be real, which means we have propagating waves. I'm gonna show you why is that later on. So k is still a progressive wave, but the lambda squared is, well, the lambda is imaginary, right? Because k squared is smaller than omega squared over c squared. But omega squared over c squared, if you think of omega being order 1, this has to be a small number. And that's why this is relevant only when k is very, very, very small. Now let's look at a situation where k is very small, but these are exact situations where lambda, not this lambda, the wavelength is very large. And this is exactly the type of acoustic waves that we're looking here. When you have an earthquake, you're generating these very long wavelength acoustic waves. And that k there is so small that this term here is negative. So lambda becomes imaginary. Why is that important when lambda becomes imaginary? Let's see what happens when lambda is imaginary. So let's write now, if lambda, let's do it like this, we can have lambda n, which is I mu n. Or we can say that mu is simply real now. Okay, so this is real. In other words, if lambda n is imaginary, what we get now is omega squared equal to, gonna have, let me do it by steps. So we're gonna have g I mu n. I'm gonna do one more step. So we have g lambda n times hyperbolic tangent lambda nh. Okay, so this is the general solution. Actually, I could also have written that here because we have many modes now that solve the dispersion relation, not only one mode. So omega squared is I g I mu n hyperbolic tangent I mu n times h. Well, what is hyperbolic tangent of I mu n h? Is I tangent mu n h. So this is omega squared minus, we have I times I minus g mu n tangent mu n h. So this is the dispersion relation now with the case where lambda n is imaginary. So mu n here is real. Now this is the dispersion relation. This is the dispersion relation in the case of the surface gravity wave. And this one is for acoustic gravity. You might say, well, it's a big deal. It's almost the same dispersion relation. Well, it is a big deal because here you don't have hyperbolic tangent any longer. It is just tangent, which means you have an oscillatory function now in depth. So if you go back now here, you won't have a hyperbolic cosine. What you will have is a cosine. So if I rewrite this now, so this is for the gravity, this is gravity, and now we write for acoustic gravity. then what you have now is phi equals, everything is the same here, minus I. I'm not gonna even write that down, it's just gonna write one thing, that hyperbolic cosine is no longer hyperbolic cosine, we're gonna have cosine mu n z plus h. Which means now the velocity potential is no longer decaying with depth. It's oscillatory in depth. It's everywhere in these 4 kilometers of depth, or the ocean depth. And this is important because in the example before, when I said the pressure, for example, when you talk about surface waves, if you just go deep few meters, it decays exponentially, you won't feel anything. But now the picture is different. In the case of acoustic gravity waves, it's oscillatory also in depth. So they would actually be, if you look at this picture here, they would actually be everywhere here. They affect the pressure or the induced velocities, unlike the surface gravity wave. So this is a big deal, okay? And the other difference is that now, because it's a tangent now, you have many solutions to this dispersion relation. So it's not only one solution. Here you have only one solution. Okay, if you try to solve this, you want to solve it graphically or numerically, you would see that you have one solution in this case. But here, the picture would be like this. If you solve graphically, well, let's make it more precise. So the asymptotes. So if you plot one side, which is, for example, the tangent, and you plot the rest on the other side, this is how you can find the intersection, and these intersections would be the solutions. You would see something like this, maybe. So this point, this point, this point, these are all solutions now. There's no longer one solution. There is a countable infinity of solutions now. There's an infinite number of modes that satisfy this equation, not only one solution. So this is one important thing, that when you're neglecting the compressibility, studying the waves in the ocean, the surface gravity waves, you don't see all these solutions. They wouldn't exist for you. But they do exist because compressibility is always there and gravity is always there. And this is what we do when we study acoustic gravity waves. Now, it's not over yet. We talk about lambda squared, which is basically, I can write minus mu n squared equal to k squared minus omega squared over c squared. This is what we were discussing. Which means these waves, these modes now, each one of them, this is kn, because we have many modes. Okay, so you could type here kn and lambda n. Now you look at that kn squared, which so far we assumed it's real, right? And so far it was real maybe for the first modes here. But does it have to be real for all modes? No. Look at this. Kn squared is omega squared over c squared minus mu n squared. Now initially, when you're solving for the first modes, it depends also on the conditions, on the depth and the frequency that you're solving for, and the medium, which we consider the speed of sound in water. We assume it's water. But what you would see is that as you go further with the solutions, this is increasing. So this, you can think of this as as mu n times h, something like that. Right? This gives you the tangent of mu n times h, this axis here. And the rest would be the omega squared over minus g mu n. So mu n is increasing, which means there would be a point, but these are constants. So you're looking for a constant frequency, and the speed of sound is constant, is assumed to be constant. There would be a point where mu n is actually larger than omega over c. Now at that point what happens? We still have a solution, but at that point k is no longer real. K becomes pure imaginary. When k becomes pure imaginary, you need to keep that in mind. Look at this here. This tells you how the waves are behaving in the x direction. This e to the power I kx. It's oscillatory. This is our sine function, right? As long as k is real. But when k becomes imaginary, you no longer have I kx there. You would have e to the power minus absolute value of k times x. In other words, you would have a decaying, exponentially decaying function in x. These are called evanescent modes. Okay, so when kn is imaginary, what you get is evanescent modes, which simply means that these modes, if you think in terms of the physical problem, how do you generate all these modes? For example, you have an earthquake, very large earthquake, 70 kilometers of width maybe, and hundreds of kilometers of length, and that earthquake generates a family of waves. It generates the gravity wave, the tsunami in this case, but it also generates the acoustic waves. At the higher modes, k is no longer real. It means that you get evanescent modes. Now these evanescent modes, they have no effect at large distances from the source, right? At large distances from the source, they would decay exponentially with x. In a very similar way to how the gravity wave, the pressure, for example, the gravity wave would decay exponentially in depth. We've seen this before. Now, I've deleted this now, but before we had this, well, we still have now the hyperbolic cosine here, right? This is, and lambda would be real in the case of the gravity waves. All right. So this is all about the what I wanted to tell you about acoustic gravity waves. If I just complete this figure here, so this would be the tangent mu and h, right? This is mu and h, this axis, and this line here in red would be minus omega squared over g mu n, right? This is one way, because you can't solve this analytically. You can try, you can't solve this analytically. One way to actually solve it is that you run over mu and h, right? You plot the tangent on one side, you plot the rest as another curve, and you see where they cross each other, and this is what you get. You get all these modes. So you have to solve it numerically at the end of the day. Okay, what we can do next with this type of problems, I might ask you, okay, what happens if we have different conditions? Different condition, one easy condition, for example, one simpler condition, would be that if you think of the generation of acoustic gravity waves in places where the sea surface is frozen. In other words, there is no sea surface there, right? So you have ice at the surface, and then I tell you, for example, you can assume that it's rigid. It's not a very good assumption, really, for the ice, but let's say that that's the assumption. In this case, you'd have to redo everything, right, with the separation of variable and finding a dispersion relation. You'll have a different dispersion relation, completely different dispersion relation now. You can think gravity won't be there anymore, because the gravity here came from the surface, but you have no more surface, it's just rigid, right? There's no free surface, I mean, there's surface, it's just rigid. In that case, you might think that you would actually have only the acoustic modes, but you need to do that and see. Another possibility, which is a little bit more complicated, I might show you this in one of the tutorials or in the exam, is if we had here some, if we actually want to solve the problem with the earthquake. So we assume that the bottom here is some rectangle and it's moving up or oscillating. So this is another problem that you know that the boundary condition at the bottom is not the same as the one that we have. One simple version of this question would be, what if the whole sea surface is moving up and down? Why do I say it's simple? Because you don't have this kind of discrete presentation of the sea floor, right? And in one place it's constant, and in another place it's moving up and down, or it's moving up. Now you have the whole thing going up and down. This is a simplification. It's simpler because now in this case, for example, you know that the phi dz is no longer 0, it's actually that function. It's some cosine which is going up and down. Alright, that's it about acoustic gravity waves for now.